Welcome to qnawire.
Okay, so we're doing chapter 18, problem 21. So it says a gas containing an N of 15,200 molecules, and they each have a mass of 2 times 10 to the negative 26 kilograms, has the following distribution of speeds and number of molecules here. So this is what we have on this table over here, the distribution of speeds. And it says this crudely mimics the Maxwell distribution. So that's going to be important. So for part A here, we want to determine VRMS for this distribution. So when we already have the speeds here and the proportional molecules here, we can find the VRMS as 1 over total N, all square rooted, and then the sum of the ith velocity bin, how many molecules are there, times the speed of the ith velocity squared. Cool. So now we can solve for this, and this is going to be a lot of writing here, so it's going to do 1 over n. Actually, I'll write what this is, 15,200. Okay, so this is 1,600 times 220 squared plus 4,100 times 440 squared plus 4,700 times 660 squared plus 3,100 times 880 squared plus 1,300 times 1,100 squared and plus 400 times 1,320 squared. Cool. Plug all of that in and take the square root of it, and we should see that this comes out to being 706.6 meters per second. We can approximate this to 710 for the future here. Okay, part B. Given your value of VRMS, what effective temperature would you assign to the gas? Okay, so we know that the VRMS is given by 3 kBT over M. So we can rearrange this for T, and this is just M VRMS squared over 3 kb. Cool. So let's go ahead and use our RMS and see what our effective temperature would be. So this is, the molar mass is 2 times 10 to the negative 26 kilograms. And our VRMS was 706.6. Square it, all over 3 times 1.38 times 10 to the negative 23 joules per Kelvin. Cool. Plug all that in. Should come out to be 241.2 Kelvin. Awesome. Okay, so I'm going to add a new page here for part C. So part C, determine the mean speed of this distribution and use this value to assign an effective temperature. Okay, so the mean speed here can be calculated similarly, but sum over each speed times the number of molecules in that speed bin times the speed bin. Cool. And now this becomes 1 over n times, so we have 1,600 times 220 plus 4,100 times 440 plus 4,700 times 660 plus 3,100 times 880 plus 1,300 times 1,100, and lastly, we got 400 times 1,320. Cool. And that's all divided by n equaling 15,200. So our average or mean velocity here ends up being 650 meters per second. So, oops, sorry, that's the approximate version. So if we actually plug this in, we should get 654.2 meters per second. Cool. So this is a little bit slower than the RMS, but now let's see if the effective temperature using this speed corresponds to the same effective temperature we found in part B. So for the average speed different than RMS speed, we can relate this as 8 over pi times kBt over the molar mass. So this equation is a little bit different, but again, we can just rearrange for temperature here. So temperature then becomes pi times m times the average squared over 8 kb. So let's plug this in. So we have pi times 2 times 10 to the negative 26 kilograms times 650. Oops. This is 654.2 squared all over 8 times 1.38 times 10 to the negative 23 joules per Kelvin. And this was meters per second, the velocity. Cool. So if we plug all this in to our calculator, let's see what we get. This is 243.6 Kelvin, which is very close. If we go back to the first page here, we had 241.3 Kelvin. So this is just roughly around 2 Kelvin off. So these correspond and are very consistent since they're just average rough estimates here. Sweet.